Okay, so this is going to be an introduction, but you know, kind of maybe adapted to the crowd here. So I'm going to try to give some intuitions about how the Zcash protocol works and how SNARKs work. Okay, so the Zcash protocol. Let's go for a second to Bitcoin and think of it through the following analogy. So right, the main object there is the unspent transaction output set. And you can think of that as some bowl that everybody can see what's in the bowl. And this bowl contains everybody's unspent coins. And what is a coin, right? A coin is like an address and a value. And let's assume for simplicity that all coins are $1. Right, so at some given point in time, these are the current unspent coins. Alice has 2, Bob has 2. And so how does payment happen in Bitcoin when you're thinking about it like this? Alice wants to pay Bob, so she creates like a new Bob coin. She puts it inside the bowl, and at the same time, she takes out an Alice coin. And the idea is that since everybody's looking at the bowl, everybody can see that, yeah, she really took out one of her coins and she put in what she took out, so everything is fine. But of course, you have there's no privacy in such a system at all because everybody is looking at this bowl. So in Zcash, you can think of it that we replace this bowl by an opaque box. So you can't see into the box. This is just for the presentation. And think of this box as having you know, a small opening on the top. So this is a box that you can drop things into. But you can't take anything out once it's in, and you can't look inside. So and also think that we've added to each coin some random serial number. We've chosen some random number and added it to the coin. But think of all these coins still as $1 coins. So the big difference so far from Bitcoin, one big difference is that, you know, once something's inside the box, you can't take it out. And of course, you can't look into the box. All right, so we need some way to distinguish between spent coins and unspent coins, right? So we're going to add next to this box a list. This list, everybody can see the list. And what does this list contain? It contains the serial numbers of all coins that have been spent up to this point. So say at a certain point in time, out of these 5 coins, only this coin of Alice was spent. So this list will contain just this number, 421. And right, this serial number, it's just a random number. It doesn't give you the ID of the coin holder. Okay, now the question is, so how does Alice pay Bob in such a system? So you know, like in Bitcoin, she's just going to create a Bob coin. And she wants to now drop it in the box. But before she drops it into the box, we ask Alice to write a new number on the list, a number that's different from what's on the list so far. And what is this number Alice is writing on the list? it's a serial number of some coin of hers that's still unspent. So, for example, if Alice is going to use this coin to make this payment now, she's going to add this serial number to the list. All right, so basically the idea is, instead of preventing double spending by taking spent coins out of the bowl, we prevent double spending by requiring unique numbers on this list. But of course, at this point, this could all be nonsense, because we don't see into this box. So how do I know that this number that Alice is writing on the list is not some completely random, made-up number that doesn't have anything to do with anything? And as you can guess, the answer in 2 words is zk-SNARKs. So Alice will somehow use zk-SNARKs to prove that this number she's writing now on the list is really a serial number appearing on some coin in the box, a coin that says Alice. So that's the Zcash protocol in 3-4 minutes. And now I want to give you some intuitions about zk-SNARKs. So I like the most, this is a kind of advanced definition of SNARKs I heard Zuko Wilcox give, that a SNARK is a bunch of words scientists put together, so their initials will spell SNARK. It's an advanced crowd, so I can use that definition. It corresponds very closely to something Silvio Micali called computationally sound proofs somewhere in the beginning of the 90s, but SNARK is more tweetable and retweetable than computationally sound proofs. So I want to give you some intuition about what I see as the 2 main ingredients in making a SNARK. And the first ingredient is that we're going to move our statement to the world of polynomials. Why are we going to do that? Because basically, if you tell a lie in polynomials, you need to lie most of the time. And just as a historical anecdote, this kind of idea, it appeared first in a really great breakthrough work that what this work allowed us to do is say there's a Sudoku puzzle that there's no solution to. And I want to efficiently prove to you there's no solution to this Sudoku puzzle, right? Forget zero knowledge for a second. If I wanted to prove to you there is a solution, I would show you the solution. Say I want to prove to you there's no solution, I want to do it quickly without you having to go through all the possibilities. So this classical work of Lund, Forno, Carl Finissan allowed to efficiently prove what's called co-NP statements of the form, for example, there is no solution to this Sudoku puzzle. So if you tell a lie in polynomials, you need to lie most of the time. Let's give a concrete example of what I mean by this. So say, for example, the lie you wanted to tell was, this program here that I starts from 0, and 10 times we increase I by 1. I want to tell you the lie that this program outputs 11. So now I'm telling you, I want to tell you the story of how this program ends up outputting 11. So I tell you the story of its execution. of how the state changed, how the value of I changed. And, I tell you the story, well, I was 0, and then we had this plus plus command, so the state of I became 1. And then again, we had another plus plus command, the value of I became 2. I continue, you're getting bored, you see I'm not lying, it's just some formality. And then when I see you're a little, a little bored and not listening, I say, and then suddenly at this, there was a point where I was 6, and then, there was a plus plus command, I became 8. I slip that through you, and then you wake up a little, and then I continue not lying, and then, I was 8, there was a plus plus command, it became 9. So the point is, when we're talking about program executions, if slipping in one lie is enough to successfully make a completely false statement. I only need to lie in one place to get a completely wrong conclusion. Okay, but now the idea, and this is kind of the basic important idea in SNARKs, the first of them, is suppose I tell you now, all right, tell me the story of this program executions, but tell it to me as a polynomial. What does that mean, tell it to me as a polynomial? I'm saying, well, so what is this story? I can think of it as 10 numbers, right? The 10 changes in the state of I, in the value of I. So, I have 10 values, what's called Lagrange interpolation. There's some degree, at most 9, polynomial that gets these 10 values, that at these 10 time points will output these values. So I tell you, find this polynomial and, tell me its values. But do me a favor, tell me its values not on just these 10 points that correspond, to the program execution. If you've already found this polynomial, just write to me what its values are also on other points. And you could say, why the value of this polynomial on other points? What does that have to do with the program? Well, just do me a favor and write them for me. And you say, okay, so say you weren't lying. So what is the true story? I always changes by 1 at any time point. So I need a function that x equals 1 gives me 1, x equals 2 gives 2, x equals 3 equals 3. What's the degree at most 9 polynomial that gets these values? It's not too hard. It's just the polynomial, the constant 1 that always returns 1. And how does this polynomial behave on the numbers 11, 12? What is f of x, f of 11, f of 12, f of 13? It's just 1. So if I'm not lying, this is what I will give you. But now the important point is that say I am lying, and just at this one point, that I wanted to falsely claim that at this one point I grew by 2 instead of 1. So the point is that now my lie will manifest a lot very clearly. So now I need to find a degree 9 polynomial that gets these weird values, 1, 1, 1, 1, 1, then suddenly 2, and then 3 more 1s. So you do what's called Lagrange interpolation. You find such a polynomial. This is just an approximation. It's going to look something like this, 0.00 something times x to the 9th. And again, on the points 1 to 10, it's very close to the true thing. But the point is that now outside this range, the lie is going to become very clear. The values of this polynomial are going to be very, very, very different than the correct one. So the point, again, with polynomials, in other words, is that once I force you to tell me a story in polynomials, if you want to check that I'm lying, it's enough to check basically at a few random points, or even one random point. Because my lie, when I'm telling the story in polynomials, will manifest almost everywhere. All right, so that's, and the second main ingredient in SNARKs is what we can call homomorphically hidden verifier challenges. And before saying what I mean by that, let me say what I mean by a homomorphic hiding. So this is a term I kind of thought of, but then I saw that in the crypto literature it corresponds very closely to these things called k-linear maps and graded encoding schemes. And this is very similar to homomorphic encryption, which I'm sure you've heard the term. So what does a homomorphic hiding mean? Well, it's some mapping E that it has two main properties. So one property is that if I show you E of x, it's hard to find x from that. So that's what hiding means, right? If I show you E of x, it's hard to compute x. The reason I call it hiding and not encryption is that there's no decryption key. There's not necessarily a way to get, even if you have there's no key that lets you get from E to x back to x. That's why I call it hiding instead of encryption. So that's the hiding part. What is the homomorphic part? The homomorphic part, what does that mean? It means that if I say give you a hiding of x and a hiding of y, well, it's a hiding. You can't get x or y, but you can get other hidings of arithmetic expressions in x and y. So for example, I give you the hiding of x and y, you'll be able to compute the hiding of x plus y and the hiding of x times y. Small note, I'm simplifying. You can't actually get anything like this. We don't know, so it's going to be some E prime here instead of E. All right, so that's basically the idea of homomorphic hiding. Now, how does this, and the idea in our context, what this allows you to do is this thing called blind polynomial evaluation. What does that mean? It means, say that the prover has some polynomial, right? So let's think, where were we at? We were at this stage where we know, okay, if I force the prover to tell me the story in polynomials, it's enough for me to check him at one random point. But there's a little chicken and egg problem here of who goes first. Because if I say to the prover, okay, I'm going to check you at x equals 13, what's your polynomial? The prover can craft a lie that looks good on x equals 13. On the other hand, if the prover goes first, he said, okay, I'm sending you all my polynomial. We got two problems with that. One problem is, right, SNARKs, the S stands for succinct. We want small proofs. These polynomials of the prover, they're going to be huge. And the second problem is we'll lose zero knowledge. For example, in Zcash, the prover polynomial, it contains all the information on the addresses, the values of the transaction. And so the kind of the clever way people figured out how to solve this chicken and egg problem is, okay, the verifier in a sense will go first. He'll give the challenge point first, but he won't give it in plain form. He'll give it in this homomorphically hidden form. And what does that do? That, I'm glossing over a lot of details, but basically that creates a situation where, on the one hand, since it's hidden, the prover can't adapt their answer to the challenge. They can't choose a polynomial that will work well on the specific point of the verifier because it's hidden. But on the other hand, since it's homomorphically hidden, the prover can still, if his polynomial is p, can still compute the hiding of p of s, just where s is the challenge point, just from the hiding of s and some hidings of powers of s to be completely, to be more accurate. How is the time situation? I got basically one more slide. I'm good, all right. It's actually a trick if you want speakers to go fast. Don't show them how much time is left because they'll assume there's, well, maybe it depends on the speaker. But I'm guessing it made me go a little faster. So that's the basic idea, and I want to tell you one more thing about, people call SNARKs moon math. So where's exactly the moon in the moon math? And in my opinion, the real magic is in these things called elliptic curve pairings, which were developed by mathematicians who didn't probably know or care about cryptography. They cared about like the Riemann hypothesis and proving things about prime numbers. And so elliptic curve pairings are where a lot of the math magic happens. This pairing, it gives you this thing. You have two groups, G and what's called the target GT. And the discrete log is hard in these groups. So if I show you g to the x, you can't find x. I show you g to the y, you can't find y. But this pair of groups, these groups, they have this magical property that you could say partially contradicts the classic Diffie-Hellman protocol. So basically, this pairing map, what does it allow me to do? If you give me g to the x and g to the y, I can compute from that. I can't compute exactly g to the x times y, right? That would totally contradict computational Diffie-Hellman. But I can, in this other group, what's called the target group of the pairing, in that group, I can efficiently compute x, y to the exponent. So for some generator of this group, from these two guys, I can actually compute h to the x times y. Okay, so I think I'll just open. Any questions about, by the way, anything Zcash related or not just the talk? Tamer, okay, yeah. What exactly? So we had the Zcash example. Yeah. Yeah, let me go back. Is the fact that it's Bob's coin hidden as well? So what is the throwing of that coin? What about it is also not known? Can you repeat the question? All right. So in this example where Alice is paying Bob, how hidden or what is hidden about Bob's coin? So the sender, like Alice, will know the value of the coin and the address of the coin. Like she'll know it's Bob. But this serial number, like the way I did it here, so for example, Alice does know, she made this coin, so she does know the serial number, the 627, And when Bob spends it and writes 627, Alice will know Bob spent her coin. In the real Zcash protocol, only Bob knows this 627. Because this 627, it's actually going to be some combination of Bob's secret key and the coin.
So how do I prove that the coin with this serial number is on the list? Like what proof, ZK proof do we produce?
Okay, so what you have actually is, so you have, you publish, when I create the Bob coin, I publish the hash of the coin, or a commitment to the hash of the coin. And everybody stores this Merkle tree whose leaves are the hashes of the coins. And also, this list is public. So Alice will prove, when Alice spends this coin, she will prove, I know some, coin, such that if I, and some path in the tree, such that if I take the hash of this coin that I know, and I follow this path of hashes, I will reach this root that we all agree is the root of the tree of all the coin commitments. And at the same time, Alice will prove this. And she will also prove, and this coin that I know a path to the root, the serial number, or as we call it, nullifier of this coin, is what I wrote on this list.
So does that mean that the entire Merkle tree is an input to the ZK function?
No, so just the root of the Merkle tree. So the root of the Merkle tree is what's called a public input to the circuit, and the path from your specific coin is a private input to the circuit.
Any other questions?
Hi there. So just going back to that example when Alice is sending a zero-knowledge proof that she owns a coin that is part of the Merkle tree. How does she create Bob's coin if she doesn't know what the nullifier is because she doesn't know the secrets?
So, so the nullifier, or what I called your serial number, yeah, let's call it nullifier, is a hash basically of the coin that Alice does know and Bob's secret key. So Alice doesn't know Bob's coin, Bob's nullifier, but she doesn't need to know it. It's only important that when Bob spends the coin, he will know the nullifier because he will need to publish it and prove that it's correct. But an important point here is that when Alice creates Bob's coin, she doesn't actually need to know the nullifier. All she needs to convince us is that the value of, she doesn't need to know the value of the coin, and that's all. She just needs to convince us that the value of this coin that I've dropped is not larger than the value of the coin I've added to the list.
Yeah, sorry, I'm a bit slow, just off the plane,
Sure.
sleep deprived. But does that mean that, does Bob need to give Alice a bit of information in order to make that coin?
Just his address. The coin is basically address, value, and some randomness that Alice chose to make the hash of the coin more random.
Okay. I think I understand. Cool, thanks.
We have time for one more question, if there is one.
I think you got over there.
You mentioned something interesting, that coins can have different values, and then you can spend a coin with, like, you can transfer it to another coin with lesser value.
Yeah.
Is this exact protocol of Zcash?
Yeah, so in the actual protocol, I can add a few numbers to this list in a transaction, and I can drop a few coins to the box. And then in the circuit, I check that the total value of coins I've added to the list is larger or equal to the total value of coins I've dropped in the box.
Is this larger equal actually used to hide the value transfers? Because otherwise I could track, like if somebody spends exact same amount of coins, like I could try to build an algorithm to track the origins of the funds. Is this used or not?
Oh, sorry, I think I said larger or equal for simplicity. I think it's actually that's a good idea maybe to use that for some extra hiding. But I think I should double check. I think it's actually exactly equal and everything else like goes into the transparent pool if there's any change.
All right, thank you very much. Let's give Ariel a big round of applause.
Thanks.